Okay, there are a few functions that you have to know really well. You have to know everything about them, how they're built, how they are graphed, their domain, their range, their end behavior. The first one is the quadratic function, the squaring function that you learned about a little bit in Algebra 1. All right, this is a parabola, and every input that you put into it, it gets squared when it comes out. So if I put in -1, out comes +1. If I put in 0, out comes 0. If I put in 1, out comes 1. If I put in 2, out comes 4. All right, so when I graph a parabola, it looks like this. It's got a vertex, which is this lowest point, and then there's a point at 1, 1, there's a point at 2, 4, and then I can keep going even if I don't have my table all filled out. 3 squared is 9, so I'll have a point at 3, 9. And then similarly on the other side, -1, 1, -2, 4, -3 squared is still 9. So I have this parabola. All right. It looks like a U. It has a nice smooth curve at the bottom. Okay. The domain of the parabola is all real numbers. There's no number that you are not allowed to square. You can square anything you want. Okay. The range of the parabola typically stops at the vertex. So if I'm going from bottom to top, right, if I'm traveling upward, the range begins here at 0, and then it continues all the way up to infinity. All right. And the end behavior of this parabola, as x goes to infinity, all right, as x goes this way, then my function goes up, also to infinity. And as x goes to -infinity, right, then my function is still going up. And we will talk about how we flip this parabola and move it all around. And when you do that, the end behavior might change. But for this parent function, this function that starts all parabolas, these are its attributes, okay? The parent function for square root functions is the square root of x. This is the most basic square root function. When we are trying to figure out a graph for this guy, we're going to pick strategic inputs. Like I know that 0 is a number I can take the square root of, and the square root of 0 is 0. 1 is the number I can take a square root of, and the square root of 1 is 1. Now 2 I can take the square root of, but the output is pretty ugly. Like it's like 1.414 or something like that, right? So I'm going to pick inputs for my table here that don't give me ugly outputs, just because it's easier that way, right? So the next perfect square I come across is 4. The square root of 4 is 2. And the next perfect square is 9, and the square root of 9 is 3. So I'm going to use these points to build my square root function. I'm starting at 0, 0, and then I have 1, 1, and then I have 4, 2, which is right here, and then I have 9, 3. So what's happening is I've built kind of a sideways parabola, okay? And this is the basis for all other square root functions. You'll note that I asked for the positive square root, so this is just the positive half of a sideways parabola. If I were to put a negative sign here, well, that does a whole other thing. That's a different function. Okay, so right now it's just this positive half of a parabola right there. The domain of this starts at 0, and you're allowed to take the square root of 0, so we're going to make this inclusive, and it goes all the way to infinity. The range of this from bottom to top also starts at 0. All right. And can you convince yourself that this is not a leveling off function? This is going to grow very slowly, but it will still keep growing and growing and growing as you go to the right. All right. Think of something like 121, right? On the x-axis, the square root of that will be 11, which is all the way up here. So as I keep going farther and farther out to the right, my function will be going up toward infinity and not leveling off at some number. Okay. End behavior, it only makes sense to talk about the end behavior at the right-hand side of this, all right? That's the only one that has an end that we're going to worry about. So we say as x goes to infinity, our function is also going to infinity. All right? And as x goes to negative infinity out here, we don't really care about that because nothing's happening out here. Negative infinity isn't in our domain, and so it doesn't make sense to talk about end behavior in that direction. The absolute value function is, this is our parent function for that, which is just the absolute value of x. We think, well, what happens when I take the absolute value of a -2? I get a +2. Absolute value of a -1 is going to give me a +1. Absolute value of 0 is 0. Absolute value of a +1 is still 1. And a +2 is still 2. So what that gives us is it gives us this v. All right, we have the point 0, 0, and in either direction, all right, I have a line with a slope of 1 on the right-hand side and a slope of -1 on the left-hand side. And so this is just going to go straight out like this and straight out like this. Now, the absolute value has a point here at the bottom. We call that a cusp. All right. It's pointy instead of a parabola, which is very smooth at the bottom. An absolute value is a pointy v. The domain of it is -infinity to infinity. The range is 0 included because we're allowed to take the absolute value of 0, 0 to infinity. Okay, and there are two ends of this function, so we can say that as x approaches infinity, f of x is going to approach infinity, and as x approaches -infinity, f of x is still going to approach infinity. Our last function that we have to know, you just have to know these, all right, is the exponential function. And we're going to say the parent function for all exponential functions is 2 to the x, all right? Note that the x is in the exponent here. So if I have my input be 0, well, 2 to the 0, anything to the 0 power is going to equal 1. All right, if my x value is 1, well, 2 to the 1 is 2. If my x value is 2, 2 squared is 4. What happens if I go into the negatives? If I make my exponent -1, let's remember that any negative exponent pushes this down, it turns it into a fraction. Negative exponents reciprocate, they make a reciprocal. So this is going to be 1/2. All right. So if I input -1, I get an output of 1/2. And if I were to input -2, 2 to the -2 is going to equal 1 over 2 to the +2, which is 1/4. So -2 gets me an output of 1/4. So when I'm plotting this, I have the point 0, 1, all right, which this is the only one I think that we've done that has a y-intercept that's not 0, 0. This has a y-intercept of 0, 1. I have the point 1, 2. I have the point 2, 4. In your head, you could come up with the point for 3. 2 to the third is 8. So 3, 8 is also on my graph. As I go to the left here, -1 is 1/2. -2 is 1/4. 1 over 2 to the third will be 1/8. All right, so we get in this function this leveling off effect. And the reason that it levels off is that no matter how big of an exponent, let's say I'm letting x be -100, 2 to the -100 is going to equal 1 over 2 to the 100th power, which is a teeny, 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 tiny number, all right? That's like insignificant, but it's still greater than 0. No matter how big of an exponent I choose, or how small in this case, this fraction is going to get closer and closer to, but never touch 0. And that is how this thing we're calling an asymptote gets created. So we say this function is going to approach, but never touch 0. So that means that the x-axis is a horizontal asymptote for this function. The domain for this function is negative infinity to infinity. The range for this function, the lowest it goes is 0, but not included. I never touch that asymptote. I never quite get to 0. I'm always greater than 0. So the range will be 0 with an open parenthesis to infinity. Okay, my end behavior as x goes to infinity, my function is increasing rapidly, so f of x is going to infinity. But as x goes to negative infinity, my function is leveling off. It is approaching 0. It never gets there, but that's what it's approaching. All right, these are your 4 main parent functions. Know them, love them, let them be your friends.